impulse. Let's see, what could that mean? We're getting such a late start today. Okay. So let's think back to the bullet hitting the beach ball, which I'm not going to do again, and I noticed someone didn't come, so I'm a little worried I may have scared someone out of ever coming to physics again. But we had the bullet flying towards the beach ball, and it hit the beach ball, and the beach ball went off this way, and the bullet went off this way and bounced back, right, the after. And we decided what must have happened is there was a force on the bullet by the beach ball, etc. So there were forces between the bullet and ball, that's what we saw happen, and the force between them are an action-reaction pair from the third law. So we didn't really explicitly talk about it. I probably said it once or twice. But whatever force that the ball, let's see, this is the ball. No, that's this. Oh, shoot. Okay, we have ball and sphere and bullet and beach ball. Okay, so this is the bullet, and this is the sphere. So we have the force that the bullet applies to the sphere, and that's being applied to the sphere. And we have the force that the sphere applies to the bullet. We're not going to do math and the details. Don't worry about the subscripts. It's an action-reaction pair, right? The bullet can't push on the ball without feeling the ball push back on it, just like we talked about with Newton's third law. Okay? So now we're going to do a bullet train. Here we go. Okay. Now a different kind of bullet. Now I mean the little star kind of bullet. Okay, so the force of the bullet on the sphere here. Make this say sphere. I should follow my notes. The force of the bullet on the sphere pushes which way? What we would call, colloquially, forward, because we shot the gun forward. Okay? Now there's another force. The force of the sphere on the bullet pushes back. Right? Now, if they're an action-reaction pair, what do we know about their magnitudes? Their magnitudes are equal. Right? Practice your notation, bars around. The vector means the magnitude. Magnitudes are equal. All right. Wait, were we allowed to pick up the pledge problems? Yeah, the pledge problems are in the physics office. So go get them. All right. Oy, it's like Morgan and Burke's back there. Now, what else do we know? Magnitudes are equal. The opposite direction. These two forces are in the opposite direction. That's a property of Newton's third law, right? So we know they went boom, and the two arrows went whoop, like that. Same size, opposite direction, if you were to animate it in some modern teaching method. Where is the physics office? It's in Brockman 209. Second floor of Brockman, the big glass doors and the friendly people behind them wanting to give you a pledge problem. Second floor of Brockman. And now, what's the other thing? Okay, so this is from Newton's third law, right? Equal and opposite. But there's another thing that technically has to be true that's not really written down in a law, but it kind of, is the thing that happens, is they're applied for the same duration. Is it really, do they have to be? Yes, right? You can't push this one without pushing back. Therefore, when it starts to push, it'll start to push back. And when it stops pushing, it'll stop pushing back. There's really no way one could be pushing, the other could be not pushing at any point in time. Therefore, they have to follow the same duration, even if they're not symmetric. I had some people in my office asking, what's the deal with the shape of this curve, right? It's kind of like this, but then we said maybe it's like that. And then one of the problems, the book shows it like that. Is that real? They all could be real. The actual detailed force versus time can be all kinds of crazy things. If you had like a spring-loaded toy that doesn't go off until you hit it, you could even have something that pushes real big and then it goes away, like that. All these things could happen, but the thing that has to be true is both feel the same force magnitude at the same time. So you can get a lot of different shapes, but each one has to feel the same shape. Right? So there's 5, oh wow, we're already 5 bullets in to this bullet train here. Let's keep it rolling. Let's see what else we've got here. Those are interesting bullets. Thank you. Let's plot. Let's go ahead and plot the impulses then. The impulses that relate to this drawing continuing and bullet train continuing here. Let's plot the impulse, or the force versus time. We're going to plot FBS, the bullet on the sphere. Okay, so this is 0 in time, or this is 0 in force, and it'll just happen, right? So what it would be? It would be, well, the force is 0, and then it goes bigger, and it goes in the positive direction. And we always imply that forward is positive. Right? So it's going to look something like this, like I've just been drawing. Like that. Okay? So the impulse is just the area under the curve. We could approximate it as a rectangle, et cetera, but we have a positive j. Remember, j is a vector. And what was j? J is the impulse. J is equal to delta p. But if we think about the other one, and we're being mathematically consistent, and I know you always want to be mathematically consistent, this is 0. Now we're plotting the sphere on the bullet. So equal and opposite, what would it look like? It'll look like this, because it's the other way, right? Oh, garbage. There we go. Other way. And now, here's something about calculus, is you talk about how the integral is the area under the curve. Well, if the curve is under the axis, then the area is negative. So the area can have a sign. So this is a negative impulse, if we're assuming the right direction's forward. Right? The sphere pushed back on the bullet in the negative x direction, so the forces are negative, so the area under the curve is negative. It's surely the area over the curve, right? That's what that means. All right. All right, so bullet, here we go. So since delta t is the same, and since the curves are the same, impulses js and jb, so that means the impulse that the sphere received and the impulse that the bullet received. Right? They both received a kick. Impulse is like a kick. Since the delta t is the same, and since the shape of the function is the same, the impulses are also equal and opposite. Fascinating. So we're just going through this logical procession here, right? Every one of these makes sense and follows from pretty diagrams or laws of the universe. Okay, well, let's say this. Here we go. Okay, now it's about to get exciting. Hold on. Since j equals the change in momentum, delta p, then delta ps and delta pb, the sphere's momentum change and the bullet's momentum change, are equal and opposite. Equal magnitude, opposite direction. Whoa. Okay, so it's just a really long way of going through this bullets and thinking about doing the second law to realize delta p's are equal and opposite. Well, if the delta p's are equal and opposite, then we could write an equation, delta ps, the momentum kick that the sphere gets, plus delta pb, the momentum kick that the bullet gets, equals 0. Because they're equal and opposite, and I wrote those as vectors, right? Not as magnitudes. But since I put a vector symbol on them, that means that includes the fact that one's going in the negative direction. If I wrote them as magnitudes, I would have said ps minus pb, because I know the bullet got pushed back. But here I'm not putting that information in. I'm writing just a full vector equation that the total momentum change is the momentum change of each one. Together they make 0. Okay. And what does the delta mean? That means before the collision and after the collision, right? The change is during this impulse is when it's happening. So when you put all this together, what it means is that momentum is conserved. That's the important thing that we're doing today, or we're starting with. All right? So we have conservation of momentum. Yes?
Is momentum conserved, but it's magnitude?
Yeah, that's what we're going to show. We are explicitly going to make that happen before your very eyes. So if we go to the Principia and we translate the third law, we say to every action there's an opposed and equal reaction. or the mutual actions of two bodies upon each other are always equal and directed to contrary parts. So then we see the third law is basically saying what we're saying here. So the third law is about momentum, really. So we could argue the first law is about momentum, the second law is about the change in momentum. It takes an external force. And the second law and the third law is about conservation of momentum. They're all saying the same thing. Newton's three laws say one thing. Momentum is conserved, and it takes an external force to change momentum. It's just saying it over and over again. But when you're the first person to say it, you can say it 3 times. Because, it's better to have 3 laws. It makes you more fast. I think I told you how you got to get to 3. 2 laws aren't going to do it. You got to have 3 laws. Okay, so momentum is conserved. Oh my God, I didn't finish the sentence. Momentum is conserved for all objects in an, and here's the part everybody hates, isolated system. Oh, we have to keep up with the isolated system. No. All right, well, we don't have a choice. So what we're going to do now is talk about isolated systems and what are the rules and what does it take for a system to be isolated. Because identifying the isolated system is the key sometimes to doing the problems. You can also just blindly do the problems and probably get it right, but if you know what the isolated system is, you'll do better. All right. Okay. So I would define it as this is not brief and nice. It's a collection of objects. I usually try to make these interesting. And interactions. Right, a collection of objects and interactions where every force, oh my God, where, yeah, this is so crappy I'm going to have to charge you for it. Every force has its reaction force within, if I could write them this bad, I'd write a textbook. Within the system. That'd be rich. Within the collection. I'm sorry, I didn't want to use the word in the definition. No, within the collection. Right, so we could say, was this an isolated system? Well, the bullet hit the sphere pushed back on the bullet, we ignored gravity and everything. So yeah, it seemed kind of like an isolated system. Let's look at a few others. Now, we're going to modify this definition. We're going to add a parenthetical statement here later. But for now, let's just do this. Let's do 2 masses isolated in the universe. So they're out there somewhere, just floating along. There's no planets nearby. There's no gravity. There's no normal forces. There's no surfaces to land on. It's just sort of 2 things like this. So here's M1, object 1, and it's moving along, and in some sort of fate, some sort of romantic comedy kind of a thing, it's going to run into M2. What are the chances? It had to be fate, right? And then they're going to hit, right? Oh, that's like the sound. Oh, there's no sound because there's no air. Well, sorry. I'm not James Cameron. Okay? And then, what are we going to do? We're going to say, what's the deal? Let's see. They're going to hit. Oh, yeah. So we want to say, is it isolated or not? So how do we know? I would do a free body diagram and think about all the forces on each mass. Okay? So here's M1. When they hit, there's only one force. It's what we talked about over here. We have F of 2 on 1. Just practice thinking about your notation. And then we do free body diagrams on M2. And this one feels the force of 1 on 2. And they're isolated in the universe. I can't think of any other forces. That's really all there is. Okay? So, is this an isolated system? Yes. Isolated system. Sometimes people like to draw like a dotted line around it. Right? And say, this is everything in the system. All the forces are in the system. All the objects are in the system. So, isolated system. Okay? No gravity to worry about. Okay, so so another definition that might be good for you is third law reacts only is one way to think about it. Let's see. Actually, in physics, in the physics community, if there's like a couple that doesn't ever get along, they're always fighting about everything, we call them a third law pair. You know, those two guys, I don't want to go out with them. They're a total third law pair. They'll fight all night. But there's so few couples it hardly ever comes up. So if you ask anybody about that, they'll say, I've never heard that before. But it happened once. So now let's do two masses on a frictionless table. Okay. And now we want to be more real. Okay, we want to keep this like legit, normal, real world stuff. So here's the frictionless table, so we'll pretend it's ice. And I'm going to make them both like peanuts, like this. There we go. So this peanut here, I'm going to regret this, is going this way. And this peanut here is going that way. And it's the same thing. Then they're going to react with each other. They're going to hit. And they're not going to break open or anything. Right? They're sliding along. And they're going to bounce back. But they're on a frictionless table. So now, let's do the FBD of these nuts here. FBD of these two things here. Sorry. A 14-year-old writes my material. So F21. So we have the force of nut 2 on nut 1, F21. Right? But we also have mg pulling it down. Wait a minute. Okay, well, that's cool. M1G, we have the normal force on 1. There's the FBD. And they're legumes, I know. Okay, just let me have my fun. How do you know if the objects bounce off of each other? What if they stick together and move in the same direction? Just wait 30 minutes. If you can hold on for 30 minutes, we're going to talk about that. But right now, everything we're talking about bounces off of each other. But when they stick together, they still have an action-reaction pair. It'd be harder to draw. Okay, so that was number 1. Here we go, number 2. It feels F12, right? The force of 1 on 2. It also feels M2G, and it feels N2. So it's more complicated, right? Let's see. So the action-reaction pairs, if I try to draw, you know, this around it, do I have an isolated system? Well, in the x direction, check. It's isolated. Because look at those x forces. The only x forces we have are an action-reaction pair. Let's look in the y direction. Okay, now we have a problem. So do we have, if I draw the dotted line like that, do we have an action-reaction pair in the y? No, we don't. Hopefully you remember from third law, the normal force and the weight are not an action-reaction pair. So if we wanted to make a system, the system in the y, to be isolated, we'd have to put in the Earth, the entire Earth. Oh my God, the system just got big. And we'd have to put in the table that's holding these nuts, right? And then the thing would have to go all around the entire Earth, like that. And that would be really stupid, right? Then every stupid isolated pair we draw of something on the Earth would have to include the whole Earth. Nobody wants to do that, right? So what you do is that's what the parenthetical statement is about. So why? Here the answer is no. You would need the Earth and the table. Right? Because the table has the action-reaction pair for this normal force, and the Earth is for the weight. So what you would do, what you can do in the real world of solving physics problems is for the dimensions you care about. Dimensions you care about. I mean, you care about your grade. For the dimensions that impact your grade that you care about. Okay? I don't know if you really care about the horizontal dimension or not. That's more of a philosophical question. Okay. Okay, let's see. So when you do a 1D problem, sometimes you'll see a book will really obsess with this and draw the Earth in the system. Sometimes you'll see, well, they just did that 1D problem. Where'd the Earth go? This is the reason. It only doesn't matter for each one. Okay. So now we're getting close to doing some problems. Good. Okay. All right. Let's recall this. Let's recall something that we said just minutes ago. Momentum is a vector. Momentum is a vector. So therefore, it can just appear. Momentum can just appear even though it is conserved. You are at 3 stages of realization of physics. You either say, yeah, I know that, or you say, whoa, or you have no idea what I'm talking about. So you're in one of those 3. We won't do a show of hands. What we're going to do now, to maybe get us all to whoa, we're going to demonstrate it. So now is when I need someone that is a skater, about the same mass as me, or willing to have your mass revealed relative to mine. Not pregnant and does not have a heart condition, and is willing to touch hands with me. It's not that much. That's got to have it down to, oh, good. Thank you very much. A 125 student came down. What's your name? Jackson. What college are you from, Jackson? McMurtry, where they keep their self-respect in the corner of the commons. Okay, excellent. Okay, so here we go. So me and Jackson are both on a frictionless surface, basically, right? So these things are very easy to fall. And all we're going to do is push our hands against each other. And I didn't derive the equations first, but let's do this first. And then you have to stay while I derive something. You can sit up front. What is our momentum right now? 0. Now let's push, and we're going to go backwards. Ready? Go. What is our momentum right now of the system? 0. Because it's a vector. Let's do it again. Right? That was so fun. So my bearings are a little oily, or a little frictiony, because our masses are the same. All right, let's do it one more time. Our momentum right now is 0. The momentum of the system is 0. Okay, now let's push. What's the momentum of the system now? 0. But we have momentum now. Right? We created momentum, but it's still conserved because momentum is a vector. Okay, now wait here. I'll post the notes. Now let's think, what if we had different mass? Let's do the math real quick. You want to do the math? No, you don't want to do the math. Okay, I'll do the math. Okay, I'm asking too much, but hang out for a second because I'm going to run back and make our weights different. Right, so here is the second person. There we go. And here, P equaled 0. And then after we push, we both move back, right, at V1. And this one, too, I guess that's me. I need to slow down. Moves back V2. So what would happen if our masses were different, or we didn't know it's just going to be 0? Well, let's see. We would start out P initial equals 0, and then we push P final equals 0. But let's write out what is P final. Let's do it with magnitudes. Right, so we're going to call my direction positive, even though I was going backwards. Okay, don't think about that. Okay, so mine is M2 V2, and then his direction was back. So I'm doing magnitude, so I'm going to put in the negative M1 V1, and that has to equal 0. So we want to ask ourselves, how fast am I going, say, because it's all about me here. I mean, that's what this whole class is all for me. Then we're going to say, let's solve for V2. V2. And you can see this comes over here, and we divide through, and we see it's basically a ratio of our weights, right? So V2 equals M1 over M2 V1. Okay? So it looked like there we went about the same speed at the very beginning. Mine is kind of frictiony. But what if we made our weights very much different? Let me get my big masses. I forgot to bring them out. Here we go. All right. Oh, this class is so dumb compared to last year. Oh, my God. Okay. All right, so now I'm going to add like 40 kilos to mine. And the question is, who's going to go faster now? Okay, here we go. One more time. One more time. All right. And now maybe you can see, here we go, push. Oh, he went faster. Why did I go slower? Because his mass is now a lot smaller than mine. Okay, totally makes sense. Thank you. Very nice. Let's hear it for someone who came. Someone who managed to come down without being too frightened of me. Okay. I had hand sanitizer, but I can't find it. Okay. Let's see. Where are my notes? I'm really tired now. Oh, damn. Okay. I'm like you guys. Damn it. Okay. Okay. So what we have now is to think about, okay, that was a case where we created some momentum. Let's get rid of that. Now we want to do a numerical example, more numerical than just that. So we're going to solve a complicated momentum problem. Okay, it's hard to make a real complicated momentum problem because it's kind of like this every time. So we're going to blend it with some kinematics and make it real world. Okay? So the question is, if I stand on the thing and shoot this, will I get a kick backwards? So let's find out. Let's see. Oh, it's jammed. Oh, let's see. Air cover ain't going to be here for a few minutes. Here we go. Okay. Let's see. Now it's just a warped floor. Check that out. Okay, this building is not level. All right. I didn't go anywhere. No. Nothing. Why? Because these darts are so light, right? I was going to fill one full of lead to see if I could get myself to go, but I ran out of time. So we'll fill one full of lead next time. So what we're going to do is a problem, and think back to when I told you about how I'm a terrible dad and I don't go to the dad's club because I don't want to shoot a shotgun, right, with people. So we're going to do that as a problem and say, if I were to shoot a shotgun here, would I move? What is your intuition? You think I would move? We're going to go through the numbers. We're going to do after the break because I'm almost out of breath. But I'll tell you a quick story. You ready? Quick story? I would never shoot a real shotgun in here, would I? No. But you know they used to. So there's something in your book called a ballistic pendulum. And we don't do it yet because it's energy. And you shoot a gun into a block of wood and you see how high it goes. And Dr. Dunning used to fire a rifle in here during class. This is like the 70s and the 80s. You may have heard Rice was wilder. Well, not just in the colleges, okay? Like the muzzle was inside of a tube. Nothing could possibly go wrong. And they had the rifle, one piece was here, one piece was here. They assembled it, they put in the bullet to try to make it safe, and they would fire a rifle. And I asked Dunning why they stopped doing it, and he said 1 year, it made him very nervous. 1 year after he fired it, somebody went, ah! Like they got shot. And that just nearly killed him. And he never did it again. I asked him to do it for the online class with no one in here, and it was too traumatic. He could never do it again. So ask Dr. Dunning about shooting a rifle in this class. Okay, let's take the break early because I got to think about this, and I don't want to break this in the middle. Okay, let's keep going. We've got to do the shotgun problem. Very exciting. This is the only sort of complicated problem I'll do this time, but we'll do some problems next Thursday because you'll have all this fresh on your mind. Okay, so here we go. So we're going to do the shotgun blast and ask, would I move? If we take some typical shotgun parameters here. Shotgun is a gun. Let's see. So here we go. I'm on a low friction surface. I'm standing on some platform on a low friction surface, such as my wheels, say, for example. And I'm holding a shotgun like this. Sorry to make this so violent here. And I don't know, it looks like that. I'm not holding it against my shoulder. Oh, no. And there it is. I've got a complex here. So I've got a bullet that's going to come out of the shotgun at 500 meters per second. Is a typical shotgun bullet velocity. Let's see, what is that? That's the bullet. There we go. And the mass of the bullet, typical shot mass is 30 grams. Right. The length of the barrel of my shotgun is 1 meter. Wow. That's convenient. Okay. And I think that's all we need to know. And I weigh 70 kilograms as usual. 70 kilograms. And we'll make up, let's say because we're on wheels, let's say the static friction coefficient is only 0.1. It's not the normal thing. Really nothing is sliding here. We're on wheels, so we'll call it 0.1. Okay. So we just want to know is if you consider the bullet coming out this way, would I end up going this way? Would I go back? Because I didn't go back there. It looks like we broke conservation of momentum. Bullet flew out. I didn't move. Right? We can't break conservation of momentum. So maybe, though, it's just because the bullet was so light. Okay, so let's go through it in terms of momentum. What is the initial momentum? I'm just sitting here. Nothing is moving. Nothing at all. Pi equals 0. Right? There is no initial momentum. What is the final momentum? The final momentum, Pf, well, that's what we're going to calculate. No, it's 0. Right? As long as we're an isolated system, and we are, so we're just doing the x direction. So we don't care about gravity. We don't care about normal forces. We just care about forces this way. So the one other force this way, in addition to the impulsive force, might be some friction. That's what we got to check to see if maybe that's why we didn't move. Okay? Okay, so here we go. Let's see. First, let's see how fast I should go then and see if it makes sense. So we don't really have to do a bunch of kinematics to figure that out. We just have to conserve momentum. So let's see. Let's say the bullet is going forward, so 500 meters per second. And 30 grams is 0.03 kilograms, right? Okay. And let's do magnitudes. We know I'm going to go back. I'm not going to go forward. When we get into weird collisions where you don't know what's going to happen, you do components because you don't know what the value is going to be. But right now, we know what's going to happen. So we'll just write everything in terms of magnitude. So since we're talking about my magnitude v, I'm going to put in the negative sign. Okay? And then we say, oh, that's 70 kilograms, right? And then the v that I'm looking for, the velocity of me, whatever, jh, right? There we go. And those have to equal 0. Because this is the change in momentum. I'm sorry, this is the total momentum. We're adding it all up. So this is PF. If you're not sure exactly what we're doing here, we're saying PF equals 0. Okay, so you solve for that, and you just get a little number, and the velocity is, the magnitude of the velocity of JH is 0.21 meters per second. So that implies that if I blasted a shotgun while standing on that thing, that's how much of a kick I would get. So, you know, not like flying out of the room, but also not 0, like I would be moving. 0.21, you know, a fifth of a meter per second. Okay. Now, really, I would be knocked off center. This is assuming a simple 1D system where everything's a point mass. What would really happen? My center of mass is here. It would hit me in the shoulder here, and I would probably fly off because we would apply a torque. But we don't want to think about torque, so let's not think about that. But in reality, I would need to have it right on my center of mass. So hold the gun like that. That'd be weird. Okay, but here's the sort of the other question is, but would it overcome static friction? Because this would imply I should have moved with the Nerf bullet. I just should have moved a lot slower. Maybe I was moving so slow you couldn't see it, but I wasn't. I wasn't moving at all. So it may be then that the force wasn't enough to overcome static friction. So another thing we can do with this problem is we can figure out the force. All right? So let's figure out the force. Let's see. What do we have? We have delta P. Don't we? Yeah. Because we know the change in momentum. We went from 0 to 500 times 0.03 or 70 times 0.21. Same thing. Right? We know we have delta P. So therefore, we have a delta P. We have J. Right? So we know what J is. We know that J equals the force average times delta T. Right? So we need, let's see, we have this, but we need the average force to see if it overcomes friction. And also, we don't really even know delta T, do we? All right, so here's our problem. We don't know either one of those things. One of our trivial things would just be, here's the impulse, and here's delta T, find F. You know, we put a few of those in there. So we have to go to kinematics, right? So we go to kinematics to get delta T. That's why we told you the length of the shotgun barrel, right? So then you say, okay, let's do kinematics to get this part. We say, well, what do we know? We know VF was 500 meters per second squared, so we're probably going to do VF squared equals VI squared because we know we accelerated for a distance, d, right? The bullet must have accelerated from rest to 500 meters per second in 1 meter because that was the length of the gun, right? So 500 squared is 0 squared plus 2a times 1 meter. That's meters per second. All right? So if we solve that, 250,000 divided by 2 is a is 125,000 meters per second squared. Wow. That's really fast. The bullet feels a lot of g-forces. If there's an ant on the front of the bullet, there is no longer an ant on the front of the bullet. Okay, so now we have A, but we wanted delta T. But we also have X. We know how far it went. So we just do more kinematics. We say delta X equals 1/2 AT squared. Right? So we're getting grown up here. I'm not writing X naught plus V naught T. Right? So we know it started at the origin. We know it started with no velocity. So that's 1/2. Let's see. So X is 1 meter. It went a meter. 1/2 of 125,000 meters per second squared T squared. So we solve that. And we get 4 milliseconds. T. Something very small, because the acceleration is so big. So that's what we need to know to think of this as a momentum problem. We need to know how fast the interaction was. Okay? And then we'd say, okay, we could do it like F average delta T, then we're done. Or we could think about, whoa, what about the real force versus time curve? What does it look like for a shotgun? I have no idea, okay? It's probably not a nice, even whatever. All right, it's probably not just a nice pull. Let's see. So there's a blast, and the chemistry has to happen. And then the pressure gets really high, and it pushes the bullet with the hot pressure gases, and then they start to decay. So it's probably something asymmetric like that. Who knows? But the point is, we're trying to figure out would it overcome friction or not. So if we do average, we're going to get a lower force, and then we'll find out if that overcomes friction, then we're fine. Anyway, we always do an average. We didn't give you some crazy shape. Or if we give you a crazy shape, it'll be easy. It'll be geometry. It'll be like triangles. Okay, so we just plug that in here. So we say, okay, we know the impulse was, we could do 500 times 0.03, or we could do 70 times 0.21. Those are the same, right? So we can say, go back to the impulse definition. We say 500 meters per second times 0.03 kilograms equals the force average times 0.004 seconds times 4 milliseconds. I know you can't see it. There we go. 500 times 0.03 equals force average times 0.04. This is just the definition of the impulse. All right, going back to here. All right, so we solved that. And what do we get? 3750 newtons. 3,750 newtons is the force that the bullet felt on average, and therefore that's the force I would have felt on average, pushing me back. But only for 4 milliseconds, right? So not for a long time. So is that greater than the friction force? Well, yes. Oh, I left my subscript on. Sorry. Then, of course, it is. So the force of friction, static friction for me, is less than or equal to, it can only go up to mu s 0.1 times my mass times 9.8, right? Because this is the normal force in the y direction, right? I'm not moving in the y. We're just skipping over that step. So 0.1 times that is very small. So the friction force can only get up to 68.6 newtons. And the gun, the rifle applied 3750 newtons. So yes, I would move backwards for sure. Okay? And I know because I've shot a lot of shotguns in my life. I used to go hunting in Kansas when I was a child, and my dad used me as the hunting dog. So like, we'd come up on some brush where there were some pheasants, and he would have me go walk into the brush and scare up the pheasants, and he would shoot them over my head. Yeah, that's why I don't hunt anymore. Sort of had he never shot me or anything. Why does the average force need to exceed friction instead of the maximum force? So the point I was trying to make is, so this was just sort of me ad-libbing here. So we just do the problem with average force. We have no knowledge of this actual shape. However, the answer we got would say, well, if 3750 exceeded the friction, I bet you this is going to exceed the friction because it's bigger than even 3750. That's what I was saying. That's all. If we had found friction was here, then it would be ambiguous. It'd be like, well, the average force didn't exceed friction, but the peak might have. But I knew that it was going to come out this way. So that's what I mean. The peak is always higher than the average. That's the only really thing you need to take away from that. The peak is always higher than the average force because of how we define things. Okay. Okay, so what we're going to do now is move a little bit into collisions. Things running into each other. Oh, wait, we have one more momentum thing to do. Okay, so has anybody ever seen a watermelon drop before? Surely in high school, somebody made you drop a watermelon off the building and you didn't know why. No one's ever dropped a watermelon? No. I see one person vaguely, slightly admitting they dropped a watermelon like that. All right, well, we're going to drop more. Do you want the high drama part with the music, or do you want to just watch it drop? I was afraid of. What about my hammy acting? Do we have to watch? I have to leave the room. That's the only way I can get through this. Okay. Let's see. Here we go. So we're going to drop a watermelon off of Rice Stadium. Here we go.
Not because it's easy, because it's hard.
All right. Here we go. It's not easy. Boom. Okay, we'll get to the important part in a minute here. So there's the physics part we'll talk about in a second here. Oh, okay, let me get back to the physics part. Here we go. Where's the physics part? Ah, damn it. I don't want to see that again. Okay, we need the part where it makes a perfect circle because we're going to think about momentum real quick right there. Pretty good. Okay, so if you think about why, you notice how it made a perfect circular splat, right? It was a beautiful circle. Why does it make a beautiful circle? Well, it's just an example of the conservation of momentum, right? So it's like this. So if the watermelon is falling this way, right? It clearly has a bunch of momentum going down, pz. So pz is increasing due to gravity because it's got a force from gravity speeding it up, and gravity is pulling the Earth up so that the net momentum is staying constant. I'll get to office hours before we stop. But what is px? 0. What is py? 0, right? So this is the z direction. There's x, and there's y. So those are both 0. So when it splats, suddenly it gets lots of momentum in the x and the y, but it has to sum to 0, right? So this is 1/2 of the watermelon. This is 1/2 of the watermelon. But in this direction, px still has to remain 0. So every piece going to the left, there has to be a piece going to the right. Every piece going up, there has to be a piece going down. Every piece going off this way, there has to be a piece going off that way. And that's why it makes such a perfect little circular pattern. This is just for fun. They don't learn anything from that, except how fast it hits. And now I know a high school physics teacher who makes the students take a video like this and track each of these pieces and estimate their mass and velocity from the video and confirm that it really is 0. Okay? We can actually relate this to the Higgs Boson. So we talked about this year's Nobel Prize. Last year's or 2 years ago's Nobel Prize was this is how particle physicists find particles, right? As they look for missing momentum. We know about the particles we know. The universe conserves momentum. So if we track every stupid particle flying out of the LHC, track all its momentum, we say, is there any momentum missing? If there's momentum missing, that's the particle that we don't know exists. We don't know how to detect it, but it tells us, oh, there's a particle going off this way that is missing. So we put on a new detector or figure out what it could be, and theorists write a bunch of papers and press releases and blah, 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 right? But that'd be like this. If you saw this track, and you saw in this segment nothing is moving out, you would say, oh my God, there's a new watermelon particle that's not detectable by the camera. And you would say, wow, that's exciting. Okay. Oh, I'll have to see it again. Oh, that is the slow motion. Okay, we're done with that. Let's make that go away quickly. Okay, so let's see. So now what we're going to do is talk about collisions. Like between the... Oh, and then somebody may ask, what's the question that we always get is we didn't conserve momentum in the z, did we? Maybe there's a missing watermelon particle in the z. No, but we did give the Earth a kick. We changed the Earth's momentum when I had the watermelon hit the Earth. It actually shifted the Earth a little bit. I had to get a permit to be able to do that, but I did it. I made sure somebody on the other side of the Earth was also dropping a watermelon at the same time. You know, all the standard whatever. Okay. Okay, so now let's do collisions then. So we've kind of been doing collisions. Right? We've had things running into each other, but we haven't been like formally doing collisions with math. And as someone is excited to hear about, letting things stick together. Okay, so that's a special kind of collision we got to look at. All right. Did we do the break already? Oh, shit. Okay. You guys are so pathetic. A difficulty with momentum. Before we get into it, let's see, what was I got a text that made me say something? What was it? Oh, yeah, office hours. So, no, there won't be, but Dr. Roberts is going to do his normal Tuesday ones on Thursday. So they'll be all Thursday afternoon. And then I'll ask Hannah what she wants to do. Before I ask Hannah, would anybody come on Monday? Show of hands if you might come on Monday. So a few people would be here. Or I could have her maybe go on Friday right before the homework's due. Either way, whatever, yeah, okay. Well, I'll ask just Hannah what she wants to do. It's probably roughly equal attendance either way. But Dr. Roberts has officially said he will move his to Thursday, okay? And mine will still be Wednesday. I'll be back. No, mine are Thursday. Oh, shit. Me and Roberts will not be at the same time somehow. Anyway, a post will be made about everybody's shifted office hours, but we are going to see what we can do. And the other one is about the exam score and should you drop or not. No, you shouldn't drop. But if this is a critical question for you and you're going out of town because of the weekend, you try to find us in office hours. I'm booked. I'm busy until 5 today, but tomorrow I have some time. And Dr. Stenson, you could email us and set up a time. So if you want us to attempt to guess what your grade will be, not that we really can. It's more of a counseling session, but we're happy to do it. Right? But to give you some idea historically how people do. But yeah, we're happy to do that because we understand add and drop is Friday. Okay, a difficulty with momentum problems. Okay. Mass walks into a bar. Here we go. Mass walks. You have to write that into bar. All right, so we got a mass here. M1. We got a bar like that. M2, right? So they're going to crash into each other. And the mass 1 is going at VI. Okay? And I keep talking about them bouncing off of each other, and we have two equations, and we're thinking about the forces. But then, let's see, the final part of this will be, what does mass 1 do? It might bounce back, V1F, and the bar might go this way, V2F. V1, I guess I'll say 1 initial. Only this one was moving at the start. But really, this one could have been moving at the start. It could have been coming at it, V2I. So what if you wanted to solve in detail and solve for those two velocities, the final velocities, just with momentum conservation? We've been doing lots of problems. We've been giving you more information. We've been telling you things like the masses and how fast things were going. What if we didn't tell you how fast things are going? What if we just had two masses and we crashed them into each other? I forgot to get them. What if we had two cars and they just crash into each other? If we have both initial velocities and both masses, we should be able to know what's going to happen. The universe is deterministic. It's not really, but let's pretend that it is. Okay? So we should be able to get it. So let's look at the math. Well, we have one equation that we could use. And that is, for an isolated system, we have the momentum conservation. If we have m1 times v1i plus m2 times v2i, we just need m1 times v1f, and we need m2 times v2f. Okay? So what we have is what I like to call two equations and two unknowns, T2, T-E-T-U, two equations, two unknowns, all right? But now we have something much worse. We have one equation, and we have two unknowns. Oh, no. We have what do I call this? We have T-ow, two equations, one unknown. You say, T-ow, oh, what are we going to do? So what we're going to do, we have two equations. Oh, that's why it didn't make sense. Yeah, what do we have? Let's make up the new word. Yeah, well, this would also be bad because it might be overdetermined. We have one equations, two unknowns, OE2. That's not good. This has been wrong for years. Oh, well. Okay, so what should we do? What do? We could use energy. So if you have the third edition of the book, it does energy first. No, wait. If you have the fourth edition of the book, it does energy first before momentum. And the third edition did momentum before energy. That's why they did a new edition, is to justify a new edition, because they just switched those two. But that's not till next week. All right? So is there any other solution to this problem? Or are we just done? There's a solution. And the solution is we do a special kind of equation where the masses stick together. Right? If the masses stick together, how many final velocities are there? Just one. And I think I have this right. We have one equation, one unknown, which is ouiao, which is French for I can do it. Let's see. Check it on Google Translate. Really, that is what that means. Okay, so let's set up this kind of equation. This equation has a name. It's called a perfectly inelastic collision. That doesn't mean something dirty in French, does it? I didn't look it up. It does? Okay, good. Perfectly inelastic collision. So why it's called perfectly inelastic collision will be clear when we get to energy. I'm sorry, not next week, in 2 weeks, when we get to energy. So elastic means it conserves energy. Inelastic means it loses energy. Perfectly inelastic means it really loses energy. It loses the most energy you can possibly lose and still obey the laws of physics. Okay? So it kind of looks like this. We have the mass M1, V1I, and we have the bar M2. Oh, I'm on the wrong page. Okay, here we go. I'm just an actor. I don't actually know what I'm doing. And we have the mass M2 going this way, V2I. Here we go. All right. So we just have to conserve momentum. So once they come together, then it's going to be one object, M1 plus M1, M2. And they're going to move. V final. We can just call it V final. Okay. Let's see. Yes, what is T2, OE2, and UAO? Okay, don't worry about it. Okay. It's 2 equations, 2 unknowns, 1 equation, 2 unknowns, and 1 equation, 1 unknown. It's not important. It's just what keeps us all awake, or an attempt. Okay, so let's look at initial momentum equals final momentum. Okay, initial momentum. Now, oh, this is important. Okay. Oh, my God. Okay, when you just look at this, do you know which way it's really going to go for VF? You don't really know, do you? Right? It could be that this one is really heavy and really fast, and it's just going to barrel through that one, and it's going to go this way. Or it could be this one is really fast, but this one is really heavy, and it's kind of fast, and the whole thing's going to barrel this way. So when we do these equations, we don't know V directions. Usually, V direction, so use components. Okay, we're not going to do it with magnitudes. We're not going to insert the signs, because these collision problems are usually much more unknown. When we were shooting the shotgun, I knew we were going to go back. I knew the bullet's going to go forward. We put in the negative sign, but we're not going to do that now. So we're just going to say M1 times V1 is the initial. I guess we can say initial. That's its initial momentum, plus M2 times V2I. Right? Now you say, that's crazy because I drew it this way, but this could be a negative number because it's just the component of a vector. Okay? We could put the vector hat on it, but it's 1D. Okay? And also, it doesn't have to go this way. Could they still hit if it was like this? Yeah, if this one's going faster, it'll eventually hit that one. Right? So they don't have to be coming at each other. So even on the initial case, you don't necessarily know which one is positive and negative because we're trying to write this for any situation. That has to equal, what's the momentum final? M1 plus M2. And then V final. 1 equation, 1 unknown. Yeah. So we solve it, and we get VF equals M1 V1I plus M2 V2I over M1 plus M2. Okay? And that's the answer. And oh my God, I forgot to bring out the inelastic colliding cars to show you how this works. So we're just going to have to draw it, or I could. Oh, and I'm out of notes. And I could run and get them. We want to go get them. Okay, 30-second break. Let me go get the cars. Let me get the cars if I can find them. 30-second break. Where are the cars? Oh my God. Okay, that was real. Yay, the collision cars. Here they are. You're all still here. Okay, good. Let's see. So what we have is, we had a good question about, so here they are. There's no friction. There they go. Look at that. Wow. Okay, so how do we make an inelastic, how do you make them stick together? Velcro. All right. To you, Velcro is this old thing. It was actually invented while I was alive. I remember when Velcro was new. Okay, so we're going to look at this equation and see if it makes any sense. We're going to see if it makes the right predictions, because it usually does. Okay, so those two things have the same mass. So let's do a few cases and see if we can plug it in. Okay, here we go. All All right. So let's say we have the same mass, and it should slow down by a factor of 2 when they hit, right? Because let's plug in the equation. VF is what? If we initially have just one moving at VI and the other not moving, then it would be M over VI over what? M plus M, 2M. So it should slow down by a factor of 2 if they just crash into each other and stick. This is only if they stick. All right, here we go. So I'm going to go at this speed. Oh, damn, okay. That's not the good one. Here it is. This is the... Okay, yeah, these match. These are the two masses alone in the universe that are destined to be together. Here we go. This is the love story. Oh. There, it slowed down by a factor of 2. Now we're going to go fast. It slowed down by a factor of 2. Wow, it worked. Okay, what if we have them come together at the same speed? See, physicists are into love stories. We're not as repressed as you think that we are. I once knew a physicist that loved her husband so much, she almost told him. That's how, so V1I and V2I is that way. So let's say they're going in the opposite direction, same mass, and same mass but opposite direction. What are we going to get? VF. Let's plug it in. These are components now. All right? So this one, we'll just say it's going at V. Or just, well, the point is they're going the same. So I'm getting the same subscript. They're both going at VI, just different directions. But since this is a component, let's do magnitudes. Sorry. Okay, so now this is a problem where we know the initial sides. We're going to put magnitudes into this formula, but we're seeing the sign tells us this side, so this is a component. Okay, this is why these problems are tricky. The algebra is not hard, but keeping up with signs is tricky. So as I say, sometimes you do magnitudes, sometimes you do components, sometimes you kind of mix it together. Okay, and you have to, because if we just do components on this side of the equation, we're never going to capture the fact that it's moving this way. But then we're going to let the sign tell us what's going on here, if there is a sign. Because in this case, we have M times VI component minus M times magnitude minus M times VI magnitude over 2M. Of course, this one is 0, right? Because these two parts cancel. So if I send them at each other with the same velocity, after I let them go, you're going to shout out the total momentum, the numerical total momentum. You're going to shout it out in any unit. 0. Yay, and it stayed 0. Look at that. The total momentum is 0. Whoa, it's still 0. Still 0. 0. It's never changing. 0, 0, 0, 0. Look at that. Woo-hoo. Oh, shit, now it's not 0. Okay. Now you see how it works. That totally made sense, right? Are we still going? Okay, so let's do another case. Here we go. I have detailed lecture for the next part, but I figured doing these examples might be better. Let's just do one more. And let's think about what if we make their masses different? Now it's going to get interesting. I planned this way ahead here. Okay, so now that would just slow down more, wouldn't it? Okay, so if one weighs more and they come at the same speed, which way is it going to go? Let's plug it in real fast. The heavy one hits the light one. M. Let's say 2M. But they're both going at VI, same magnitude, like that. Let's see if we can plug that in and see which way the whole thing is going to go. So we'd say VF equals, this is M, magnitude VI is positive, minus 2M, magnitude VI is negative. So the magnitude of VI, I put the negative on there because it's going negative, over 3M, right? 2M plus 3M. So you can see the answer is negative. It's going to be negative 1/3 VI. So if that really did double the mass, which is approximate. But the point is, it should go this way. The heavier mass will win, and it will go that way. So here we go. Oh, yeah, they're both going. Oh, shit, they're both going at the same direction. Oh, this is not going to work. Okay, here we go. Did you see it started to fall that way? Okay, same direction. There we go. It went that way. I have other masses, but I don't want to leave again. Oh, I could have put this on top of it. Okay. Oh, well, here we go. 2M. I am an experimentalist. Here we go. There we go. So it slowed down. You couldn't tell exactly a third, but it did slow down. Okay? So that's examples of the conservation of momentum. So the last thing to think about, this is more of just a thinker. I haven't decided if we're really putting this in the class yet. We're still, want to see how far I got today. It's really more of a big picture, interesting thing. Going back to the concept of the center of mass. Okay? So now you can do inelastic collisions, collisions where things stick. We'll do elastic in a couple weeks, and it's more complicated. And the demonstrations are more enlightening and dramatic, if you can imagine. Okay. Let's see. Exam uploaded on Canvas seemed to be a lot more about circular motion. Does that make, I don't know. I have to think about it. Yeah. Okay. Okay, so we've been doing these two masses in 1D, right? So we have mass here, and we have mass here. And they move, and maybe they hit each other, etc. Weird stuff happens, okay? But let's think about what is the center of mass of this thing. Like, say this is the origin, and that's plus x. And they're sitting at different positions. Before we talked about this point called the center of mass that was somehow important. Before it was what? It was where gravity acts. And it was also if you throw the thing in the air, the center of mass kind of acts like it's the point particle. It's where if this thing is a point particle, that's acting like where the point particle would be. And it'll just move as though it's a point particle. That's actually true even for two masses. Really? Really? Yes, I swear. Let's write the formula for the center of mass. 1 over the total mass times x1 times mass 1 times its position plus mass 2 times its position, right? That was where the center of mass would be, right? This is the origin. This one, if it's really big, it would drive the center of mass this way. If this one's really big, that formula will push the center of mass that way. If they're the same, it'll be in the middle, right? Okay. So what we could do with that formula is bring the big M over here. All right, equals M1 x1 plus M2 x2. So all it is center mass, brought it over here to the left. The big M is on the left now. Total mass times the center mass is equal to those two. But now let's take a derivative. All right. What is the derivative of M x cm? It's M times the velocity of the center mass. The total mass times the velocity of the center mass equals mass 1 times velocity 1 plus mass 2 times velocity 2. So these are the individual momentums here. But this is the momentum of the center of mass. Right? So what it's telling you is that you can think, well, just like in Newtonian forces, when we thought of the center of mass as a special place where the force acts, it's also this special place where you could treat this as a point mass and it'll just go. So in all the collisions I did, if we thought about what's the center of mass doing, it's just moving. It's not doing anything. Okay? So like when this one was still and this one was moving, the center of mass was slowly making its way this way, but it was going slower than this mass, right? It was collapsing down to this position. So it's going slow, and then when they collided, it moved slower. The center of mass just went the whole time. It never budged, right? Because the center of mass of this system, there's no external forces. All the little bumping into each other, those are all internal forces. But the center of mass, it just glided the whole time. Okay, so we'll do more examples when we get to elastic collisions, but you can kind of think of it here. So, okay.